let me introduce myself. My name is Nadia Kunyasari. I'm from SMA Negeri 3 Bogor, and I will present a research titled Application of Simple Magnetic Suspension on Washing Machine. Washing machine is commonly used as a home appliance. It operates in certain angular velocities. During extraction phase, washing machine top rotates at a relatively high speed, which creates unbalanced condition. Therefore, excessive vibrations and inconvenient noises tend to emerge. Although vibration is normal and unavoidable in moving parts because of manufacturing standard, it needs to be minimized by the suspension system. Elasticity that exerts from the suspension system would dampen the oscillations. Spring coil primarily functions for the suspension. As time passed, it has evolved and developed to benefit from another material. Magnetic suspension is an essential technology for manipulating objects with a mechanical contact using a repulsive magnetic force. According to Mesta study at 2018, magnetic attraction at equilibrium is the same as its repulsion. This research is intended to compare the effectiveness of both mechanical and magnetic suspension by observing the restoration abilities. Factors that cause them are hopefully identified by analyzing the number of times each suspension oscillates, as known as frequency. This research will also prove and demonstrate the utility of magnet in diminishing the vibrations. Can magnet alternate spring coil in the suspension system? How is the frequency proportion of mechanical and magnetic suspension? Which suspension type is more effective to function in vibration reducer and why? This experiment had been conducted thoroughly on Wednesday, October 14, 2020 at 3:15 p.m. Western Indonesia time at Taman Sari Persada Street, Bogor, West Java. The washing machine prototypes have several sections and specified as shown in this image. The top is 15 cm long and supported by the 4 feet. Both top and feet are made of PVC pipe. This observation was performed to centralize this oscillating suspension system in reducing vibration. Therefore, the top is static, or not be able to spin as in operation of commercial washing machine, and the load is in motion instead. Materials that used for mechanical suspensions are steel spring coil with 2 mm in diameter, which slightly downscale from ones that are sold in the markets, detained by the pipes as pointed by number 1 and 2 in this image, to get the springs to be movable only in straight direction. The magnetic suspension is assembled as in this image. Magnet material that has been used is neodymium or NdFeB. The neodymium magnet is known as the strongest permanent magnet material. The magnets are physically dimensioned with 20 mm in diameter and 5 mm in thickness. The use grade for this observation is N42 with 36 gauges at a distance of 40 mm, repelling force up to 0.08 lb, and pull force up to 0.19 lb. Each foot has two magnets attached on the surface of smaller pipes on number 7 and 4 with the same poles facing toward each other as shown in number 5, so that there would be a repulsion and levitating effect. The bigger pipes that have been pointed out by number 6 are used for maintaining the linear position on the proper magnetic field. At the initial condition, spring coil rested at a length of 7 cm. The magnets were in the equilibrium position where there was no external force and motion applied. At this position, the air gap between the two magnets was 4 cm. The average room temperature when taking the experiment was 29 degrees Celsius. The true load mass 110, 200, and 260 grams were added and moved gradually onto the prototypes. While its mobility was generated, a slow motion featured camera had been used to perceive displacement of the suspension in maximum compression phase. There is no exact measurement for the speed because of the limited feature in the motor. The analysis is managed after acquiring the displacement data from the experiment using the following correlating laws and studies that build up some equation on theoretical approach. Due to the occurring centripetal force upon the load, the second law of mechanics states that the net force equals mass times acceleration that could be implied on this equation. Force acting on the suspension system affects the change in length or its displacement acts to oscillation as mentioned in the following equation. The top mass has measured to be 0.24 kg and R is 0.05 meter. Hence, those values can be straightly substituted into this equation. Sujit at 2018 studied that coefficient K, or stiffness value, is determined by dividing the load weight over the suspension deflection. By computing the whole specified elements like the main diameter, the modulus of rigidity, and the coil diameter, and also the active turns, we can obtain the stiffness value and convert it into the meter unit. Since magnetic suspension doesn't use a physical spring, we have to distinguish the equation into this. Fm stands for the magnetic force. To determine the magnetic force, we have to use the online calculator KJ magnetic because there's no specific equation to calculate the repulsion force. We have to convert the magnetic force in lb to Newton by multiplied to 4.448 Newton. Then, substituting the equation 5 and the equation 3, there obtain a new equation. Variable x in this equation is eliminated. The magnetic force itself has already represented a displacement. Both equations have variable f, or frequency. As mentioned in the objective, that frequency is very useful to determine the potential causes of vibration. This table has shown the displacement that occurred on magnetic suspension is greater than the mechanical suspension. The average displacement for magnetic suspension is 7.67 mm, while the mechanical one is 3.67 mm. The elasticity of the suspension has been represented on the data and will be investigated more by calculating the frequency. This table has given information that there are drastic discrepancies between the mechanical and magnetic suspension. The percentage of the mechanical suspension's average frequency by the total frequency average of both suspensions is 0.0052%. By theoretically inspecting the elements inputted to the derived equation, the mechanical suspension is immediately having more determining factors compared to the magnetic one: coil diameter, modulus of rigidity, and the amount of spring active turns. In spite of those, the springs used in this experiment have also been examined to be too stiff in a small-scale prototype. Magnet has restored a bigger displacement than the mechanical one. The higher frequencies have magnet obtained indicates that the suspension damps more vibration. Meanwhile, the mechanical suspension has much lower ranges of frequency due to its corresponding factors, which tend to decrease the flexibility and effectivity in reducing the vibration. So, magnetic suspension is more effective in minimizing the excessive vibration on the operating washing machine because it doesn't get influenced by the material rigidity as spring coil does. The top needs to be able to spin to equalize the work of the regular washing machine. Spring material used for the observation needs to be scaled lower in order to avoid the ratio incongruity in comparison. Moreover, the repulsion strength of the permanent magnet should have observed more. Electromagnetic induction can replace the permanent magnet, so that the repulsion rate and initial air gap will be able to change by setting up the electric current. Load comes in various mass that may require the different control to resist. Taking advantage of fluid behavior, hydraulic pump can also be an alternative for washing machine vibration reducer. More, the establishment of these ideas will prospectively be well applied to complex manufacturers or large-scale scientific projects other than the domestic appliances, such as particle accelerator, since its operation also involves the circular motion and electromagnetic steering. Thank you very much for your attention.